Technologies and Performance. He holds a master's degree from École Supérieure d'Électricité Paris and a PhD in computer science from the University of Versailles in France. So with that, let's welcome Dr. Khan.
Good morning. Thank you. I appreciate the opportunity to talk, particularly at this place where there are such a superb and smart group of engineers and scientists looking at the biggest challenges in the wireless area. So, I'm told by my friends not to start a presentation by showing a curve or a graph. I'm also told not to start a presentation with the bad news. Actually, they recommend me, like we saw over the dinner talk yesterday, to start the talk with a nice video. So today I'm starting my presentation with the bad news, with the curve, and I don't have a nice video. So, we are all familiar with the 2008 financial crisis and the depression that followed. And I think we are over that depression right now. But another less familiar crisis that happened in 2008 was at that point the demand for mobile capacity vastly exceeded the capacity that even the latest mobile technologies could provide. So I call this wireless engineer depression era or a disgrace era. I refer to era before that as the pride era, because at that point, we were able to develop technologies and stay ahead of the demand curve. But later, it turns out that was not due to that we invented fantastic technologies. It was that until 2008, the demand in mobile data was slower. And we became complacent as we thought having incremental gains is adequate. And in 2008, with the surge in the number of smartphones and the demand that followed, we were caught off guard. And this gap continuously widening, and we are still, in this disgrace era where the data demand is much higher than the capacity that we can provide. And I think every day we experience this. Recently I had experience where I suddenly got $600 bill for my mobile plan. Apparently there was some operator introduced some mobile cap, and then if we go over, they charge huge amounts of money. And then I decided to file a complaint with the Better Business Bureau. And if you go to that site, there are two top choices. The first one is if you have a complaint with the car dealer, and the second one is if you have a complaint with the mobile service provider. So I was ashamed that this is not the fault of the mobile service provider. As a wireless engineer, this is my fault. It is our fault. We did not develop the technologies so that we can provide the needed capacity. So what happened around 2008? To see the magnitude of that change, we can look, for example, at this picture. This is showing the debut of Pope Francis in 2013 compared to Pope Benedict in 2005 in St. Peter's Square. You can see the square is illuminated by smartphones and tablets in 2013. So, I was bragging about my job to my 9-year-old daughter and saying, I joined Samsung in 2004. I said, okay, I developed technologies that enable products in the next 5, 7, and 10 years. I told my daughter, I joined Samsung in 2004, and in 2013, everybody is using Samsung's phones and tablets. She said, Dad, no, there is one phone there in the 2005 picture. So I said, yeah, this is the old clunky feature phone you can see out there. So this shows you the magnitude of what happened around 2008 and the following years. Okay. And mobile communications, it's kind of pretty well established right now, has been the most transformative technology in the history of humankind. This technology has touched more lives than any other technology in the history. Actually, we can say that 50% of the Homo sapiens who ever walked on this planet are using this technology, because 50% of us are alive today due to population growth. So this is the magnitude of this transformation. So for many communities around the world, simple voice and text messaging is bringing about revolutions in terms of access to education, health, financial, and agricultural services. Many farmers in rural Africa and Asia are using text messaging to find the daily prices of commodities so that they can have a better bargaining position and also select between the end markets. And in some of the least developed regions of the world, such as sub-Saharan Africa, there is higher levels of mobile access than other basic services like electricity, sanitation, and financial services. For example, in Nigeria, there are 60 million people without electricity, 40 million without water, but pretty much everybody has a phone with the voice and text capability. So now imagine, but 2/3 of the world still do not have access to the internet, either via landline or mobile. So that is a big, for us, we take smartphones for granted, but 2/3 of the world population do not have access to the internet. So what if we can bring through this mobile communications, internet access, not only text messaging and voice, this will bring in revolutions in terms of education, financial, agricultural, and health services for those communities. So this transformation is more profound in the developing world, has the potential to be more profound. We move from like brick and mortar banks, schools, or other hospitals to like having access to the information through desktop and now through mobile phones. But in the developing countries, there are no infrastructure, no brick and mortar schools, hospitals, and there is no wide internet access. So this is the first time, like in those communities, maybe first time the mom or dad took a picture of their child is not with the camera, with the smartphone, because there were no cameras, no TVs. First time they shot a movie and they watched a movie can be through smartphones. So what we can enable if we can bring now the mobile internet to the remaining 2/3 of the world population. So I'm going to start with, I'm showing you some background because the title of this presentation is Path to the Network Wisdom, so I want to explain a little bit background on that. So this is the data, information, knowledge, wisdom pyramid. So when Milan Zeleny first developed that, he referred data as know nothing, information know what, knowledge know how, and wisdom know why. So data is raw symbols, numbers, or letters without context, while information put data into context. So a letter, a conversation, a documentation, novels, news, as well as the cultural expressions such as movies, music, paintings, poetry, they are all examples of information. So knowledge is the result of finding patterns in information and the ability to create new information. So over the dinner talk yesterday, I think maybe we were confusing knowledge with information. If we ask the question, how old is Barack Obama? The answer, 52 years, is information. It's not knowledge. I cannot create new information, or the machine cannot create. Knowledge is more, I can create more information. Maybe when, as a human, I know somebody is 52 years old, maybe I can say that person, if it's a male, can have gray hair and other things. I can create more information. So that is what the knowledge is. And wisdom is, over time, when you accumulate experience, you develop the understanding to find patterns and principles, and so that you can put knowledge into context, combine knowledge, and apply it appropriately, resulting in wisdom. So in summary, wisdom is more taking the right course of action with the experience, knowledge, and good judgment. So this is more like a human quality and knowledge also. But the thing is, with all the knowledge and wisdom, humans, we have invented things and machines, and they are slowly moving up the pyramid. So machines, so measurements, as humans, for us, measurements are our maybe 5 or 6 senses, maybe sight, hear, smell, taste, touch, and thermoception. And this is how, the neuro signals are created, and then the brain converts that data into information, and over time, brain learns patterns in information, and this is how knowledge is created. And over time, we as humans develop wisdom. We kind of make the right decisions. But the machines are moving up the pyramid. They are much better at measurements. I can only see visible light spectrum or can hear very narrow acoustic wave spectrum, but machines have no limits. Even cameras, yesterday night we saw that bullet firing out. I cannot see that, but now we have high-speed cameras that can see that. So, and also machines can make these measurements with higher precision, accuracy, and speed. So machines are getting better here. But maybe we are better up in the pyramid at this point. So it's arguable maybe machines now can maybe, so for example, with my camera, I take a movie, that movie is information. It's not just raw symbols, but it is information. Similarly, record a music and so on. But machine, with my phone, I can take a picture in a fraction of a second. But if I have to draw a painting or something capturing that scene, it might take several days for me to do that. So machines are much better at, down in the pyramid. So my argument here is that we should use machines or things, what they are doing better at, and then the humans contribute where we are best at, up in the pyramid. So I think yesterday, attending poster sessions, I was amazed by looking at all the different type of sensors and so on. This is all these things, sensors, machines, getting better and better. Down in the pyramid here. So how we can use this? So this is what I call our maybe transition from Homo sapiens, which in I think Latin is wise man, to this networked wisdom. So for us, before all communication access meant like people having access to information. So this is now, I'm calling it access to data, information, and knowledge. But now, more and more, things are creating data, information, and knowledge. And more people which saw user-generated content. It's not like as humans, I'm also creating more and more data, information, and knowledge by blogging and taking movies, taking pictures, and sharing all that information. So the next generation of mobile communication is not only going to be about ubiquitous access to data, information, and knowledge. As I said, I mean, that is needed. Even 2/3 of the people on this planet do not have this ubiquitous access. So we need this, but more and more, there are going to be a lot more things and people generating this data, information, and knowledge. And then we also need the ability to capture that. And now things also need to access this data, information, and knowledge to become smarter. If I have an isolated device, it cannot be very smart. But now, if as humans and things, we can also generate data, information, and knowledge, and also be able to access that data, information, and knowledge, and able to contribute it to back to everybody else. So, I mean, as a humans, I have access to not my own intelligence or brain power, but also the brain powers of other humans, and also the measurements, or down in the pyramid, all the great measurements, data, information that these things are generating. So the next generation of communication is having ubiquitous access, not only for people, but also things and machines, and also universal capture of data, information, and knowledge. And of course, everything needs to go in the cloud. This is where data, information, and knowledge can be stored and analyzed. So this is all, I mean, still down in the pyramid, DIK. So my hope here is that with all these collaborations between humans and also making use of the machines and things, we as humankind can develop some type of network wisdom, which is more than the sum of the wisdoms of the human beings, so that we can address some of the biggest challenges facing us, like energy, water, healthcare, and other. So as wise man, we have not been very wise recently, I mean, due to impact on environment and looming problems of healthcare, and water is becoming a big problem now. So maybe we need more than Homo sapiens. We need this network wisdom, I mean, a great collaboration between not only 1/3 of the humankind, but all humankind of this planet, but also all the new things and machines that can bring in value to the table. So this is just showing, I mean, the number of mobile connections going up, and the traffic going up, in particular due to increase in these streaming applications. You can see 10 times increase in capacity in 5 years, and also a lot more things. So we only have 7 billion people on this planet, but the number of machines can be orders of magnitude more. I mean, machines can help us this universal capture of data, information, and knowledge. I can have, I mean, as a human being, I cannot measure like pollutants in the environment or carbon dioxide levels, but machines can do those things. So we make use of the machines, and they bring in value to this whole big picture. And of course, cloud traffic is going to go up, because this data, information, and knowledge generated by human beings and machines need to be fed back to the network, so that it can be accessed by others. So this is maybe more familiar. What I mean, they're saying that if you cannot measure it, you cannot improve it. So how we measure ubiquitous access to information? So I have this type of metric. I mean, experience per bits per second, per hertz, per meter square, per joule, per flop, per dollar. Yeah, it's a little long. The experience is also, I mean, this is all technology, But as of our dinner talk yesterday, we recognized the importance of this experience also. I mean, this means all the industrial design, software, user interaction, algorithms, and all those great things. But this is not only for humans. Now we are also bringing in machines into the picture, or things. So we also need to see how, these things feel, kind of how they can have better access to this data, information, and knowledge. So bits per second per hertz, of course, we can do it by digital signal processing, MIMO, beamforming, and then I also need to have more spectrum, more hertz. Then I can go higher in frequency bands. This is how I can increase my available spectrum. And I also need to increase capacity per meter square, because we humans live on this planet. So over a given geographic area, I need to have a higher capacity. So I can have beamforming can give me spatial reuse, small cells give me spatial reuse. So I need all those great technologies. And low power RF devices systems, because we want to, for ubiquitous access, I'm only going to have my smartphone, which has a limited battery life, right? So if I runs out of power, there's no ubiquitous access to data, information, and knowledge. So it needs to be low power. It needs to be not that complex. We need to do most in every cycle. And most importantly, the cost needs to be lower. Because, as I said, 2/3 of the world population do not have access to the internet. And 1/3 of the world population live on less than $2 a day. That is $60 per month. That is our data plan monthly bill. So that's the only thing they can do if they spend their $60 on mobile access. So we need to bring down the cost. So yesterday I saw e-wallpaper, all the great things BWRC is doing, with the idea of bringing the cost dramatically low and so on. So this is the path we should be taking. So this was the ubiquitous access to data, information, and knowledge. This is traditionally what we were thinking about mobile communications, because it gives us access to the information. But the other part that is becoming more important now is universal capture of data, information, and knowledge through these sensors, things, and machines. So there, of course, I want to capture as much information as possible on as small areas as possible. So I need sensor device miniaturization, because these devices are going to be implants, wearables, and maybe these sensors need to be all over the place, because I want to take every possible measurement that can help me solve the biggest challenges that we are as humanity are facing: energy, even food, water, and healthcare, and so on. So, but I want to make them as small as possible, miniaturized. So this is important. Of course, as much as information on a given area I want to capture, but when it comes the time to transmit that information, I need to compress that information, particularly if it's like a video recording, because I can get orders of magnitudes reduction in the bit rate without undermining the quality by data compression. Then, of course, all this needs to be captured with low energy, or ideally with zero energy, to make it universal capture of data, information, and knowledge. Again, all this needs to be done at a very, very low cost, so that our dream of this network wisdom can come true, because any piece of information would be hugely valuable in that big picture of networked wisdom. So for the access part, what we need to do, what I call is the wireless mobile data omnification. So Omnify here stands for order of magnitude increase every 5 years. So this is little bit more aggressive than the Moore's law. Moore's law gives you maybe a 8-time increase in 5 years, but here we need 10 times increase. That means in 5 years I need 10 times increase. In 10 years I need 100 times. in 15 years, I need 1,000 times increase in capacity. So, I mean, this is not something that has not been done before. We have seen this type of over 30 years, million times increase in storage capacity and also computing power. Moore's law is pretty close to this, but only communication has been lagging. But now is the time that communication catch up with the computing and storage technologies that are already available to exploit this huge amounts of data. So if we go from 1 megabits per second in 2000 to 1 terabits per second with 6G, in 2030 we have this 1 million times increase in capacity. But as you, I mean, this is exponential growth, but as you go in the later part of this curve, the lives become more and more difficult. I mean, I'm having orders of magnitude increase in data rates, but I still have the same, I want to use the same device for ubiquitous access. It has the battery technology is not improving. That means my energy cost per bit needs to go down by 10, 100 or 1,000 times. Otherwise, I cannot fulfill my dream of ubiquitous access to data, information, and knowledge. So these are peak data rates. Of course, average data rates are lower, but in short range, the data rates can be higher. So how we can get there? How we can continue this omnification of wireless data? So a little bit history of mobile communications evolution, starting from, so with every new generation, so there has been a nice evolution of wireless technologies. Every 10 years, we have a new generation of wireless technology. So every new generation of wireless technology does three things. It improves spectral efficiency, it increases data rates using larger bandwidths, and most importantly, it enables new services. So in the 1980s, analog systems were targeted for voice communication, but then the major transition to digital communications happened with the 2G, and there was a huge improvement in spectral efficiency due to digital signal processing techniques that I could use voice codec to compress my voice signals. I can use channel equalizer to remove intersymbol interference due to multipass. I can do channel coding to correct errors. So I could now pack more voice channels in the given amount of spectrum. But digital nature also enabled text messaging or SMS service. So there was a new service with 2G. And 3G, we went to CDMA technology and used a larger bandwidths. A GSM used 200 kilohertz, WCDMA used 5 megahertz, so I could have even higher data rates. And then there were new turbo codes technology introduced that gives us link capacity close to the Shannon capacity limit. So turbo codes within a dB or a fraction of a dB give me that limit. So I cannot do better between a transmit antenna and receive antenna. We already reached the limit with 3G. And with 4G, then MIMO was invented. So MIMO was one major technology for 4G, because it turns out that Shannon capacity limit is between a pair of transmit and receive antennas. If I can have more transmit and receive antennas, my capacity can be higher and higher, as many pairs I can have. But the problem is all mobile communication, for that matter, all radio communication uses spectrum less than 3 gigahertz. So, I mean, 3 gigahertz is a 10 centimeter wavelength. I cannot have many antennas. I mean, my phone is 10 centimeters long. I cannot have many antennas in the phone. So I cannot scale with MIMO, I mean, due to the limitation in frequency. So I need to go higher in frequency so that I can have more spectrum, as well as I can use more antennas, because the wavelength becomes smaller when you go higher in frequency. So I go 28 or 30 gigahertz. I have now 10 times more bandwidth. Maybe I can now have 100 times more antennas with the 2D 1010, and this is how I can continue to scale up my data rates and capacity. But the life is not easier, because the channel characteristics are completely different at millimeter waves. as well as the RF components. So BWRC did pioneering work in 60 gigahertz technology for short-range connectivity, and now after 10 years, I think we are getting to the power levels that are reasonable in a mobile form factor, but the range is just, maybe 10 meters. But with mobile communication, we want to do several hundred meters range. That means my power levels need to go up by orders of magnitude. So I again run into this RF components efficiency. So there are big challenges that we need to solve in the RF components efficiency at millimeter waves to enable mobile communication in this band. So yeah, I don't think anybody here will ask me this question why we are going 10 times higher in frequency, because BWRC did some of the original work at millimeter waves and 60 gigahertz. But at other places, people ask me this question. So I have one political answer. I say during the space era, John F. Kennedy said, we chose to go to the moon not because it is easy, but because it is hard. So same here. At that point, United States, even now, the most technologically advanced country. So if we are not going to the moon, nobody else is going to dare to go there. So as the largest technology company and mobile as our largest business, if Samsung, we are not going to take on this challenge, nobody else is going to take on that challenge. But the other thing I ask people, okay, why do you think 30 gigahertz is a higher frequency? What is the highest frequency you can get? Did you ever think about that? What is that limit? I know people here are doing great work on millimeter wave and terahertz, but what is the highest frequency you can get to? So, yeah, oh yeah, but you can, yeah. So, pardon my ignorance here, because I'm going to show you some numbers, and obviously you will see, maybe you will say there are some problems with that, but that is not, so I'm little ignorant also here. So this is how I said, okay, you can calculate a frequency similar to what Planck did. He calculated the smallest possible length, but I can use the same three fundamental constants of nature, speed of light, Planck's constant, and gravitational constant to come up with the frequency. And now you can see speed of light is a very big number and a very big power of speed of light. And Planck's constant and gravitational constant are very, very small numbers, 10 to minus 34 and 10 to minus 11. And speed of light, 10 to 8. So you get this big number. There are already 9 zeros in gigahertz. Just these constants have, this is a theoretical number. I'm not sure if there's a practical value to that, because all these... why are you taking speed of light to the fifth power? Because these all constants have some units. In order to come up with the frequency, I need to arrange these constants in a way that I can get that... yes, yeah. So... actually, Planck did the same thing to calculate the Planck length. It's not like there is some magic there. Yes, yeah. But these are the constants. So maybe the constant I'm getting, this constant is some constant, which is the limit, right? So, yeah. But this number is 18.5 billion trillion gigahertz. So when I looked at this number, I remember from my undergrad, being in electrical engineering, so I had colleagues from mechanical engineering. I used to make their fun, like 25, 30 years ago. Photocopiers were not very, maybe to the current level of technology. There would always be a paper jam or something. I used to make fun of them. I said, mechanical engineering is not even a science. When I say make 2 copies, the electronic part, photocopier always make 2 copies. It doesn't make 3 or 4 or 1. But there is always a paper jam, always problem in the mechanical part, never problem in the electronic part. So I said, you cannot even repeat experiment. With electronics, I say make 4 copies. It doesn't say if it likes me, makes 4. If it doesn't like you, it will make only 2. It's always 4 copies. But paper jam, mechanical parts always had those issues. But when I looked at this number, I said, mechanical engineers, we design now airplanes that can go higher than the speed of sound, actually multiple Mach. So that is maybe less than a millionth of the speed of light. So maybe mechanical engineers, they already developed technologies where they can achieve millionth of the limit on speed they have, speed of light. But if this is the limit for us, we are billion, trillion times lower than that limit. So this is, maybe we need to be more aggressive and do a better job in going higher in frequencies. So now hypothetically, what does this mean if I can really achieve this? Actually you cannot achieve this frequency, but at this frequency, this photon will have so much energy because energy is proportional to, is equal to Planck's constant times frequency. This will have so much energy that it will form a miniature black hole. But so I'm not suggesting that you should start communication. So that is scary, right? So let's not do this frequency, but anything lower than this, maybe we can consider. So what does this mean? If I can achieve this frequency, so world's total data is about 10 zettabytes, 10 times 10 to 21 bytes. If I can just use 10% fractional bandwidth of this frequency, I can transmit that data in all the world's data. This also includes every word humans ever spoke on this planet, and you convert that into digital signals and store that. This also includes that. I can transmit that in 100 millionth of a second. So we humans are not good at interpreting big numbers. Another way of that is, this is the total data human beings have ever generated, including every single word we ever spoke. Not the text, but the speech, which requires more bits. And if we continue to generate this amount of data every second for the next 3.17 trillion years, I can transmit all data in 1 second with this bandwidth. And what if I can design a processor that can work at that frequency? So world's total computing power is 1 zettaflop, 1 into 10 to 21. So computer at this frequency will be 10 billion trillion times more powerful. So what I can do is all operations performed by any computing device ever existed on Earth. I'm saying on Earth because I don't know, maybe there are other intelligent lives who can do better than us, can be done in 1/10 millionth of a second. So these are all operations ever performed, this including my quad-core processor, each processor gigahertz on my smartphone running right now, any computing device ever. So another way of looking at it is all the operations ever performed on the planet Earth. If we start performing those number of operations every second for the next 300,000 years, I can perform all those operations in 1 second at that frequency. Okay, so we go higher in frequency. You as researchers are going to tell me that, we need smaller devices because my FT and Fmax, they need to, they only scale up when we shrink the devices. So how small we can get. So that is, we have the familiar Planck's length. That is a very, very small number. Everything is reversed now. These small constants are in the numerator and the big constant is in the denominator. And so the total number of transistors in the world is 1.2 into 10 to 21. And another thing I noticed while I was working out these numbers is all these three things are power of 21. Total amount of data in the world in bytes, number of flops, operations I can do, as well as the number of transistors. Then I thought maybe makes sense because 1 gigahertz processor maybe has about 1 billion transistors. So there is some correlation in these numbers, and maybe each operation is performed on a byte of data or something like that. So I can fit all the transistors in the world in 1 millimeter square, which is a dot with your pen, you make that dot, and still your length of your transistor is going to be 178 billion Planck lengths. So this is, very big number. Looks like our transistor will still be very, very big. I'm calling those transistors. I'm not sure what should be the name for those devices. Other way of looking at is, if I have a 20 nanometer transistor today, I blow it to the size of the universe, 93 billion light years. Very big number. We cannot comprehend that number. Then this Planck length is a 20 nanometer transistor within that universe. So you can imagine how big our transistors today are compared to the limits. So this is again the smallest. We cannot go smaller than that, because I will need a photon with at my FP frequency I showed you. I cannot measure length smaller than Planck length, because that photon will create a black hole. So this is where at the smaller scales, space and time is supposed to be, we think maybe is discrete. We cannot go smaller than that. So these are the ultimate limits. So again, pardon my ignorance here, but I wanted to show you these numbers so that we can think big. Nature is not providing us any limits. Why we are not thinking big? Why we are just doing incremental things? I learned that as I'm getting old, but for many young people here, I think you don't have any limits. You can think big. But humans have tendency of thinking incremental. This is I don't know, maybe 3,000 years ago. The humans, we were born and then we live and die. There was no concept of progress. So that is all we need for survival. So we are not wired to think big, only think incremental. So we have to force ourselves. What are the limits of nature? Again, this is not very exhaustive analysis, but it's just giving you an idea about where might be the limits and what we can do. So, now coming back to, we decided to go to millimeter wave frequencies, 10 times higher frequency. Again, for some people that might look like a big change, but given the limits that nature is providing us, there is basically no limit what, these numbers tell us. This maybe doesn't seem as big a step. So, at Samsung, we developed this millimeter wave system. Exactly 1 year ago, we performed a demo of this system. So it's at 28 gigahertz, 500 megahertz bandwidth, 64 antennas, because your antennas are very small, 10-degree beam width, channel coding and modulation. So we did the field trial test for this system, both in line of sight, where we can get like 1.7 kilometers range, and we still had 10 dB power headroom available. This is assuming that you can have the same power levels as the current 4G base stations. And then we did non-line of testing as well in our campus in Korea, and we can get non-line of sight several hundred meters range with this technology. Many people think millimeter wave is line of sight, but you can leverage the reflections. I think the people at BWRC know that very well, and you can enable non-line of sight communications even in a mobile environment. And then we also did outdoor to indoor penetration, because these base stations can be outdoor and then you need to penetrate indoor, and also the mobility tests at 8 kilometers per hour. So to show the feasibility of millimeter waves for mobile communication, and also multi-user to provide more capacity in a given geographical area. I can have orthogonal beams with this large number of antennas that can enable multi-user MIMO. And then we also did this a simulation in an urban environment where we model all the details of the buildings. So how the building material, every single detail is modeled to see how the signal propagates and what type of data rates we can achieve. So I have a short, so this is urban area 1 kilometer by like half a kilometer, and you can see with like 10 base stations we can cover this metro area. I'm going to show you a movie to make that.
Recently, millimeter wave technologies have drawn keen interest as a method to support explosively expanding wireless data traffic. Here, we are going to envision mobile communications using millimeter wave beamforming in the dense urban city. We modeled real building structures and architectures in Ottawa City, Canada, and deployed multi-base stations in millimeter wave bands for ray tracing simulations. For the given area in the simulation, 16 base stations with 200-meter intersite distance can provide the overall satisfactory received signal quality, and 10 base stations are good enough through the optimization of cell planning. The propagation characters of millimeter wave are analyzed to fit very well in small cell deployment. Beamforming is the key enabling technology. Once mobile station performs the initial network entry based on beam searching algorithm, then the beam tracking algorithm keeps the stable connection even in the multipath environment. When mobile station is crossing the cell boundary, multi-BS beam tracking algorithm is performed for smooth handover procedure. Sometimes the connection environments can rapidly change. In this case, multi-BS connections can be helpful to maintain the seamless services. Throughout the simulation, the user data rate was analyzed to be at least 4 gigabits per second with 1 gigahertz bandwidth, and wideband processing technologies and various beamforming algorithms would be key players to make it real.
So as you could see, you can leverage the reflections, but also when people think millimeter wave is only good for line of sight, they only consider point-to-point links. If this link is blocked, I can not get any signal on the other end, but this signal is reflected. But in the mobile communications, I have many base stations. If the base station on this side is blocked, I can always pick a signal from another base station. I can pick up reflections. I can pick up from a number of available base stations, and this, when a millimeter wave hits a obstacle, it's not like the signal is absorbed, it's reflected, it goes somewhere, right? So I can always leverage that to enable this communication. So I think I'm running out of time. There are many 5G activities, and so every new generation of mobile communications happens every 10 years, and in our view, 5G will happen in 2020. There is even a more need because now we are in that depression era, as I showed via that curve, and we need to develop this technology by thinking big to meet the mobile data capacity demand so that we can provide information to data, information, knowledge to all the human beings on this planet, and also including more and more sensors and things, not only access but also universal capture of data, information, and knowledge. So Samsung in Korea, there are going to be 2018 Winter Olympics in Pyeongchang. So we are planning to have a trial system to provide the 5G service during 2018 Winter Olympics. And we also know news coming out of Japan for 2020 Olympics. Japan in Tokyo, they also want to have 5G deployed, getting ready for those Olympics. So 5G, in our view, will be happening in 2020, and there are a lot of big challenges that we need to solve, particularly in the RF front end, and that is, I think, this sweet spot for BWRC. And also goal is to reduce the cost per bit. So, I mean, this is very, very important while also not increasing the energy consumption, so that we still can use these battery-powered mobile devices. So with that, I will wrap up my presentation. I think I ran over time. I'm not sure if there is any time for questions, but I'll, yeah.
Okay, thank you.
Mm-hmm.
Maybe one quick question.
Actually, I have 3 short questions.
Yeah.
I only get to ask one? Okay, can you say how you do the beam search? I understand the beam tracking, but you need to do an initial search to establish the target?
Yeah, so we have synchronization signals that are sent with the wider beams in the beginning. So this is how you narrow it down to a narrow beam.
Okay. Did you do a backbone, or this is just from a base station to mobile?
This is just from the mobile station to the base station.
Right.
But at millimeter waves, our view is there is so much spectrum available that you can also do backhaul using millimeter waves. And with this beamforming technologies, you do not need orthogonal spectrum. You can spatially reuse the same spectrum for backhaul as for access.
Thank you.
Yeah, thank you. So, I will be around during break time, and if you have any other questions, I'll be more than happy to address those. Thank you very much. Thank you.
Okay, before we start the next technical session, Olivia has a couple of short announcements.
Hey, everybody. I would just like to remind everybody that checkout is at noon. We have the poster session probably going to start a little late. We'll try to catch up as much as we can. But if you'd like to, you can, check out of your room, maybe the tail end of the poster session. We'll have the bus waiting in front of the lobby, so you can load your luggage on it right before lunch, or you can leave it in the hallway here, and we'll take care of it. All right. Thanks.
All right, so actually, while we're getting set up here, so this next session is going to be covering a couple of different topics. This is kind of just to give you a little bit of a selection of, some of the latest and greatest stuff happening from the student perspective. So I think the first couple of talks will be focusing on the RF FPGA project, and then after that, DJ will give us an update on some of the neural interface types of things. So just while we're getting set up, I guess we can, if anybody has any entertaining jokes or comments or anything else they want to make, feel free. No, you don't want that.
Hey, wait. You can. So can I have your phone?
Where's your USB here?
Oh, it's here. This one.
You can use this.
Maybe we can ask Farooq. So, have you guys patented the however many trillions of terahertz communication system yet, or?
You cannot patent the principles of nature, right?
No, actually, I think the USPTO is not particularly, Okay, there we go. So just maybe to briefly introduce Naichang. Naichang, this is you just finished your second year, correct?
Oh, yeah, yes.
Okay, so he just finished his second year. He's advised Bali, but he's been working closely with Bora and myself on the RF FPGA project. He's going to tell you some of the latest and greatest results on the test chip that we had taped out a short while ago.
Yes, Maybe I just use it on this mode. Just use it on this mode. I think it's okay. I don't see necessary to use full screen mode. Okay. Good morning, ladies and gentlemen. My name is Nai Jonggo, and I am a second-year PhD student in BWRC.
Today I'm going to give a brief update on the DARPA FPGA project in its first year. This project is hosted by Nokia Research Center and the 3 BWRC faculty members, Ali, Ila, and Bora. In the first year, we tapped out a transceiver, which was 3-chip package on LTCC interposers for low loss and high power and frequency reconfiguration.